All right, well, I apologize. I did it again. The video timed out on me. I had no idea I'd been talking that long. So what we were at when the video timed out was we're going to take this triangle and the unit, the thing that we're going to solve for the hypotenuse here is power apparent. And that is going to be in the unit VA, volts times amps. Volt times amps is something that you see. VA is a unit you'll see a lot of times on equipment. And we'll use that VA to figure out what size the circuit is we run. As electricians, if we know the VA of a piece of equipment and we know the voltage that's it's rated for that we're going to apply to it, we can simply divide voltage out of VA and get A left over, or current. And that's how we size our wire, obviously, is by the current. So let's go ahead and do the math on this. If I take the square root of 428 squared plus 200 squared, I'm going to have, run it through my calculator, 428 squared plus 200 squared equals a really big number. Second square root, second answer. Enter, and I get 472.42. 472.42 VA. Now, that's power, that's apparent power, but it's not in watts, it's in VA. This is reactive power here, but it's not in watts, it's in VAR, VARs, volt amps reactive. And my true power, my only true power, is what happens at the resistor and creates heat. And it's 200 watts. This is really the only power that's leaving the system, is in the form of heat. Everything else is staying in the system. It's returned to the system. And that becomes important when we start talking about the next thing we're going to talk about, and that is power factor. I'm going to erase a couple of these things because I think we know them by now. And you guys can always rewind and take a look at that. Power factor is a thing that is real important to folks who are big power users. It's also important to the power company. If I have a large operation and I'm running a whole bunch of equipment that are inductors. Now remember, almost everything that creates movement is an inductor. A motor is made up of inductors. Solenoids are inductors. A lot of things that don't create movement are also inductive loads, such as lights, ballasts, and lights. Transformers are inductive loads, which we run a heck of a lot of transformers because the big power lines deliver us power in a certain way. So all of those coils, all of those inductors, put this inductive load on our circuitry. And when I've got a lot of inductance, but not a lot of resistance in a load, I have what's called poor power factor. And power factor is just a ratio. Here's what the book, and the book has some good stuff on this. Power factor equals power true divided by power apparent. Yeah, watts over VA. That's another way some people will say it. Watts over VA is my power factor. And it's a power factor, so it can be expressed either as a percentage, because it'll be something between 0 and 1, or it can be expressed as a decimal. So in this case, let's go ahead and solve power factor here. So in this case, I've got 200 watts divided by 472.42 VA. And my power factor, if I get my calculator out, this is just a straight division problem, 200 divided by 472.42 equals, I get a decimal, 0.4233. I'm going to round it to 0.423. 0.423 is my power factor, or, expressed better, 42.3%. Now that's not an efficiency, that is the relationship between this, which is actual power that goes away out of the system, compared to this, which is the power I pay for. Right? This is what the power company charges me for. This is the actual power that goes away and is not returned to the system. So if I can change these two things, if I can make this triangle somehow make this number smaller, make this end of the triangle go smaller, all the time that goes smaller, these two lines become closer to the same length. If you think about the geometry of that triangle. This hypotenuse, as the reactive power becomes smaller and smaller, the hypotenuse approaches the size of the side that represents the resistive power, the true power. And that's what we want. We want a power factor that's close to where my voltamps, my apparent power, is close to my true power. And we'll talk about how to do that later. But that becomes important because there's another way I can express that. Let's go ahead and keep this number here, my 42.3%. And this is the one place I'm going to ask you to do trigonometry. Let's put, let's see, 428. My P apparent is 472.42. We're going to put that up there, and I'm going to erase this business down here. My power factor is 42.3%, or as a decimal, 0.423. You'll see why that matters in a bit. So, when I again am graphing these sine waves, here's my x-axis, right? Here's time equals 0, and here's my one sine wave. I'll go ahead and I'll call that sine wave my volts, right? So I'll go ahead and label it E. And I don't even care what the scale is at this point, because you'll see what I'm doing here. What I know from what's happening here, what I know about this circuit, pick a different color here. Hopefully you guys can see blue on the video. What I know is because this is an inductive circuit, we talked about this a little last time, I'm in Eli. Remember my mnemonic is Eli the Iceman? Well, I'm in an inductive circuit, so I know my voltage is going to go before my current. My current lags my voltage. So if this sine wave is my voltage, I know that my current is going to lag my voltage. So that's how I say lag, because remember, it actually comes out here a little bit more. I drew that terribly. But if this is now and this is 16 milliseconds from now, the black line happens first, right? If I'm going this direction, I encounter the black line, and it's a little bit ahead of the blue line. The blue line doesn't happen until later. Sometimes people have a hard time getting their head around that. They say, well, it looks like the blue line's out in front to me. Well, the way we're thinking about it, if this is now, this is a little while from now. And it crosses 0 a little while from now. So current lags the voltage. Well, I know that it can't lag any more than 90 degrees, right? Because 90 degrees is what it would lag if there was 0 resistor and it was all inductor. But I've got some resistance in there in my current. My current is made up of, this blue line is actually what's happening right here in my total current. My current that's going out of the source and going both through the resistor and through the inductor. It's the mathematical addition of those two sine waves that are 90 degrees from each other, right? And they come up with, the difference between those two ends up being this total current sine wave, which itself is somewhere between 0 and 90. It's always going to be between 0 and 90. And we can figure out exactly how far between 0 and 90 if we use a little trig. Now, this isn't a math class. If you happen to learn a little bit of math accidentally, or I happen to teach a little bit accidentally, be it as it may. But here's a little, I'm going to give you just a little hint in what we're doing in trig. Rather than teaching you all of trig again, all of the sine, cosine, and tangent, I'm going to say that when we want to do this, to figure out this angle, there's a way to solve what they call angle theta. And angle theta is the angle between these two. Now remember, we can talk about angles in triangles, vectors having an angle from each other, but in this case we're saying how far down the line, half of an alteration being 90, half of a full cycle being 180, how far are these two sine waves together, or apart from each other? And that's our angle theta. And angle theta equals the invert cosine of the power factor. So that thing we just solved, power factor, and we got 0.423, and you're just going to have to write this down and memorize it unless you're a trigonometry geek and can remember how to do this. But what we want to do is we want to take our calculators and we want to dump that number as a decimal into our calculator and figure out what the invert cosine of that is. And I can show you on the triangle why that's cosine, right? Because if this is our triangle, and we're solving for, let's see, we've got watts here, and we've got VA here, and our power factor is watts over VA. Well, that's going to be what? Adjacent over hypotenuse from this angle. If we're solving for this angle, then the trig function, again, if those of you who don't do trig, don't worry about what I'm saying here, is watts over VA. That would give us this angle. So to find this angle, we do the invert of this ratio of watts over VA. That's why it works. So to do that in our calculator, and the book shows you how to do this too. It even explains a little better why we do it this way, but why the math works this way. I'll tell you why we do it. I'm going to go ahead and say, let's see, clear, and I'm going to do second cosine. So my cosine button is 2 above the 8. But I don't want to just hit cosine, I want to do second cosine, because that gives me my invert cosine. Trust me, that's the one I want. Invert cosine, when I hit that, it opens up a parenthesis in my calculator, and I dump this number into it, 0.423. Enter, and I have an angle of 64.97 degrees. That's how far. So I've drawn this poorly. Right? I'm going to erase this blue line. Going back to my black, which is my voltage, if this is 0 and this is 90 and I'm looking for 64, I'm going to be a little bit closer to 90 than to 0. So that other sine wave is going to be out here, and it's actually going to lag quite a ways. That's the current sine wave. And the difference between these two is my 64.97 degrees. And that's the same thing as this angle here. This angle is 64.97 degrees on my triangle, and over here I'm going to have my var. But notice, I don't even use var in this equation, right? Now earlier I talked about if I have a series circuit, I've got 3 triangles. I've got my ohms triangle, which is made up of resistance, reactance, and impedance. And I've got my voltage triangle, which is made up of the voltage at the inductor, the voltage at the resistor, and my source voltage being the hypotenuse. Going back to the other circuits now, just talking about it for a second. And then I didn't do last week, but we could have also solved powers there. And powers would have also given me a triangle with watts, VA, and vars. Now, any one of those triangles, I could have taken the element that it represents what happens at the resistor and divided it by the element that represents the hypotenuse. So had I solved my reactance triangle, I could have said, well, my resistance over my Z, R over Z equals power factor. Because this triangle is the same. If it's the same circuit, the resistance triangle, the voltage triangle, and the power triangle in a series circuit are the same. In a parallel circuit, the current triangle and the power triangle are proportional to each other. They have the exact same proportions. They won't be the same lengths because we're dealing with different units. But this angle theta, we call here, which is represented here and represented here, I can get that out of any one of those 3 triangles. We think about it as power, though. We think about it as watts over VA or true power over apparent power because it ends up being an important thing when we're figuring out about total power being consumed or being used, being delivered to a facility. Later we're going to learn that when I throw one more element at this circuit, a capacitor, I go ahead and I move these 2 things back closer together again. This capacitor does the opposite of this inductor. And those 2 things will cancel each other out to a point. We're going to learn that later, but that's what's coming next. For now, what I want you guys to be able to do from this is to take a really super simple parallel circuit with 1 resistor and 1 inductor, and I would like you to solve for the current at the resistor, the current at the inductor, the total current, and now you've got everything you need to solve your 3 powers. I'd like you to be able to draw the triangle for the current, the Pythagorean relationship between the currents, draw the triangle for the Pythagorean relationship between the powers, and then solve power factor for me. So I want you to be able to get it all the way to what is watts over VA expressed as a decimal, or excuse me, as a percentage and as a decimal, and then dump that decimal into this formula and give me the angle. Eventually, I'm going to want you to be able to draw this as well and show me the difference between those two. Now, this wasn't the best presentation on the board I've ever done. I got a little messy there. I'm going to try and give you guys some more stuff to do. I think it worked really well giving you a practice problem last week, solving the practice problem for you, and then giving you a similar but different problem to do on your own. I feel like that made you learn it. You were able to go back and kind of cheat a little bit, not really cheating, but look at what I've done and say, okay, this is how we do this next. But I'd like you guys to be able to get your head around this. The reading is really good this week. Some of the math goes a little farther than we need to go. Do the reading. I will not ask you to do the problems in the back of the book, the practice problems, but they are great practice if you're somebody that likes to do that and wants to stay up on top of this. They will make you use that ugly formula. They'll put it together. They aren't always going to present them nice and easy like I do. They're going to make you use Z and solve for Z using 1 over the square root of 1 over r squared plus 1 over x of l squared, each of them invert. So if you're ready and willing to do that, go for it. But take a look at them. The answers are in the back of the book for the practice problems. There will be a quiz on Monday. It will be a similar problem to this. And as always, thank you for a lot of you who've done so much better at the submittals this week. And thank you for getting them in on time and paying attention to this stuff. I know this is not the easiest way to learn. This whole distance learning with the COVID thing is a bummer, but I think we're doing well in getting through it. I do have a couple of people that didn't submit quizzes last week, including one that didn't submit a final last term. So I'm hoping those folks get in touch with me. Take a look at your grades. Make sure you're not that person if you're watching this video. Watch the other videos. Email me, text me, stay in touch. Stay well. I hope I covered everything. Sorry it was a jumpy video at times, but you'll handle it.